Classifying matter. Our table of contents. In this lesson we're going to talk about what matter is made up of. Elements. Specifically we will talk about atoms and molecules and the difference between the two. We'll talk about compounds. And we'll also look at a number of different mixtures and then how also we separate mixtures. So classifying matter, one thing for us to kind of take into consideration is the fact that when we're measuring matter or elements specifically, when we're looking at the atoms of those elements, we have to find a very, very small unit of measure. And that small unit of measure is the nanometer. A length of 3 to 10 atoms lined up, one right after another, is 1 nanometer. In comparison, a grain of sand is about 3 million nanometers, and a grain of pollen is about 500,000 nanometers. So for centuries, we tried to determine what matter was made of. And then around 450 BC, the Greek philosopher Empedocles, he proposed that matter was made up of 4 major elements. And those 4 elements were air, earth, fire, and water. And this idea was actually accepted for a very long period of time. Close to 2,000 years, people believed in his theory. Now we've actually come to the conclusion through some experimentation that matter is actually made up of more than just these 4 basic elements that he proposed. So in the late 1600s we began to experiment with matter, began to identify different types of matter, and that led to us discovering around 100 different elements. Many of those elements are found naturally. Uranium is the last naturally occurring element that we find on the periodic table. Everything after uranium is actually synthetic or was made in a laboratory. An element is a substance that cannot be broken down into any other substances by chemical or physical means. So they're the simplest substances. All elements have specific physical and chemical properties, and those specific physical and chemical properties are due to the number of electrons or the number of protons that those elements contain. Elements are represented by an atomic symbol. So the atomic symbol is the 1 or 2 letter symbol that you see on the periodic table. For example, carbon has a symbol that is represented by the letter C. Oxygen is represented by O. Gold is represented by AU. Sodium is represented by Na. So it's important for us to realize that the first 2 letters of an element don't necessarily line up with what the first 2 letters are of its name. So those atomic symbols are not necessarily related to the English spelling of that element. So atoms. The particle theory of matter explains that all matter is made up of atoms. But in the bottom right-hand corner of the slide, you can see a picture of a carbon atom. It shows the electrons in their orbital paths, shows the protons and the neutrons inside of the nucleus, and then it also shows the charge that each one of those subatomic particles have. Atoms consist of a positively charged nucleus and a negatively charged electron cloud. And then each atom has different properties due to the differences in the nucleus and in the electron cloud. Molecules. Atoms of most elements are able to combine with other atoms. When atoms combine with one another, they form a chemical bond. And the chemical bonds are just simply the attraction forces that occur between 2 atoms. And then as atoms combine, they form larger particles called molecules. So this picture right here shows an example of a number of molecules. You can see where across the top of the picture it has oxygen, hydrogen, carbon, nitrogen, chlorine, fluorine. Those would be examples of elements. Those elements then combine with one another to form different molecules. A molecule is a group of two or more atoms held together by chemical bonds. So for example, water molecules are made up of two hydrogen atoms that are attached to one oxygen atom. And oxygen gas, the gas that we breathe, it's a combination of two oxygen atoms. So we actually use some picture representations of atoms in order to explain what they look like when they combine together and form molecules. So you can see in the key, the C represents a carbon atom, the H represents a hydrogen atom, the O represents an oxygen atom, and the N represents a nitrogen atom. And then in each one of these pictures, we want to identify what is the number of each atom that is present. So in the first one, for carbon dioxide on the left, we have one carbon atom, and there are two oxygen atoms combined to the outside of that carbon atom. This is the same molecule that is released when we go through a burning process. So in class you've seen me before burn paper when we talk about law of conservation of mass. And as we go through and burn that paper, this carbon dioxide is released into the atmosphere. Same molecule is released when you go through respiration. So your body is converting the glucose that is inside of your body, and as it converts that using the oxygen that you breathe, it produces carbon dioxide. Water is one oxygen atom and two hydrogen atoms. Oxygen gas, the gas that we breathe, is two oxygen atoms. And then ammonia is one nitrogen atom and three hydrogen atoms. It would be pretty confusing if we were to actually go about drawing every single one of the molecules that we know of on our planet. And every single time we were to sit down at a sheet of paper, sit down at a desk and try to explain these things, it would be very difficult. It would take a long time to draw these pictures out each time. So we use kind of a formula to represent the same thing. Whenever we're talking about carbon dioxide, we say CO2 because there is one carbon atom that is binded to two oxygen atoms. The subscript below the O, the 2 below the O, represents the number of oxygen atoms. You can see where there is no number underneath or no subscript after the C. That just simply represents that there's only one carbon atom. Water, H2O. H2, two hydrogen atoms with one oxygen atom. O2, oxygen gas. And ammonia, NH3. The N is attached to, or the nitrogen is attached to, three hydrogen atoms. So water, ammonia, and carbon dioxide, all which were seen on the previous slide, they're all compounds. A compound is a substance made of two or more elements that are chemically combined in a set ratio. Compounds are represented by chemical formulas, so we saw some of those chemical formulas. And then this picture in the bottom of the slide here, it shows a number of different compounds that can be found in our planet. We've got hydrogen, H2, oxygen, H2, or O2, excuse me. Nitrogen is N2. Chlorine, Cl2. NO is nitrogen oxide. H2O, again, is water. NO2 is nitrogen dioxide. And CO2 is carbon dioxide. Chemical formulas show the elements in compounds and the ratio of those atoms. So for example, we saw CO2. The 2 below the O, again, for oxygen, tells you that the ratio of carbon atoms to oxygen atoms is 1 to 2. If there is no number after an element symbol, it's understood that the number is 1. A different number of atoms in a formula represents a different compound. So for example, if we remove one of the oxygen atoms from CO2, we get CO. And this is the formula for carbon monoxide. And here the set ratio of carbon atoms to oxygen atoms is 1 to 1. There's one carbon atom to every one oxygen atom. When elements chemically combine, they form compounds with properties different from those of the elements. On the next slide, there's an example of what happens when copper combines with sulfur. Each one of those elements have their own distinct properties when they are separate, but when you combine them, we get new properties that emerge. So in the upper left-hand corner here, we have copper. On the right-hand side, we have sulfur. And then down towards the bottom, when those two are combined, it creates copper sulfide. So copper is shiny, reddish in color. It's hard. It conducts electricity real well. Sulfur, on the other hand, is yellow. It's kind of crumbly. If you run it in your hand or you kind of push on it, it'll usually break off into little pieces. And it's really dull. When the two combine, they create copper sulfide. And copper sulfide is black, it's really flaky, and it's also got kind of a metallic luster to it. Mixtures. Elements and compounds are substances, but most materials that we find on our planet are mixtures. A mixture is made of two or more substances that are together in the same place, but their atoms are not chemically bonded. So when we have a compound, the atoms chemically bond. They share electrons. Mixtures do not share electrons. A mixture is different from a compound. So each substance in a mixture keeps its own properties. So unlike the previous slide where we saw copper combining with sulfur, creating copper sulfide, in this case, each substance keeps the properties that it previously had, because those atoms are not combining. Also, the parts of a mixture are not combined in a set ratio. We can have certain parts of the mixture having larger concentrations than other parts of the mixture. There are two types of mixtures that we're going to talk about. A heterogeneous mixture is one where you can see the different parts. They're easily separated out. Sand from the beach would be an example of that. So you can actually take a scoop of sand from the beach, you can kind of look at it and you can see small rock pieces, you can see little pieces of shell. On occasion you can find little crystals of salt in it, and all of those could be separated apart. It would be a little bit difficult, but you could do it. A salad is another example. You can easily see the separated pieces of lettuce, tomato, onion, or any other ingredients that are added to it, and those different pieces or different parts can be separated out. A homogeneous mixture is a mixture where all of the materials are very evenly mixed. And in this case, it becomes very difficult to separate out the different parts of a homogeneous mixture. So air is a homogeneous mixture, and it's a mixture of quite a few different gases. We know that oxygen is present because we're breathing. We're going through respiration. Without oxygen, we would not be able to do that. So we know that it's present. But for us to actually go out and try to pull the oxygen out of the air, that would be impossible. A solution is another example of a homogeneous mixture. Solutions can be liquids, gases, or even solids. So here's an example of a couple of different mixtures. We want to try to figure out if they are heterogeneous or if they're homogeneous. Honey, if we look real closely there, we can't really even see any separate parts. Honey would be a homogeneous mixture, and honey would not allow you to separate out any parts. Guacamole, the dip, you can see where there's different pieces or parts added to it. You can kind of see there's little tomatoes added to it. This is an example of a heterogeneous mixture. Finally, soy sauce is another example of a homogeneous mixture. You cannot separate out the parts of soy sauce. Um, they are they are not easily separated out. Down at the bottom, we've got a thing of ketchup. And ketchup's kind of a tricky one because when you look at ketchup, you go, well, that one has to be homogeneous. It has to be a mixture that we would not be able to separate out the parts. And in all actuality, we can separate out the different parts of ketchup. Ketchup actually has tomato paste in it and water, and tomato paste and water are easily separated out, and they easily separate into layers. So ketchup is actually a heterogeneous mixture. Um, we do try to separate mixtures, and we will perform a few experiments later on where we do separate some mixtures. But since the substances in a mixture keep their properties, you can use those properties to separate a mixture into parts. Methods that are used to separate the parts of a mixture include distillation, evaporation, filtration, and magnetic attraction. So these pictures show examples of each. The first one, anytime we use a magnet in order to separate out things that have magnetic properties, we are using magnetic attraction. So for example, taking iron objects and separating them from a mixture using a magnet would be an example of magnetic attraction. Filtration is an example where we use some type of filter to get the liquids to separate out from any other parts of the material or of the mixture. Usually we're going to separate solids from that mixture. Evaporation. Evaporation occurs when we either leave a liquid out in the open air where it just simply is allowed to evaporate itself, or we can even boil the substance, causing evaporation to occur. What will happen is all of the liquid water will evaporate off, or whatever the other substance is that's making up the liquid will evaporate off, and it will leave behind the solid components that were mixed into it. So in this case it shows salt water. If we were to boil off all of the water itself, it would leave behind the table salt. And then the last one is distillation. And distillation is a little more complex. And this takes liquids, and the liquids are separated from each other by heating them up to the temperature at which one of the liquids boils. The liquid boils into a gas, and then the gas cools, forming the separated liquids. So we saw that in the video that we watched in the Hunting the Elements video, where they were boiling the urine to try to get potassium out of it. So that would be an example of distillation.